So we have to start with question number 6 today. Perindopril is a drug used to treat heart disease. Okay. Here we got the structure. State the number of chiral carbon atoms present in one molecule of perin. Okay, chiral carbons you were telling me, Abdullah. Let me check. Yes, can anyone else tell me how many chiral carbons it has? So this is a one chiral carbon. This is the second chiral carbon. This is the third. This is the fourth, and this is the fifth. So if you see, there are 5 chiral carbon atoms in this structure. Okay, so I will write 5. Next part. Suggest one benefit and one disadvantage of producing a drug such as perindopril as a single pure optical isomer. Okay, so that's what we have studied in the chirality, that when we get a single pure isomer, which is actually, so it doesn't have a side effect. So, or it has a lesser side effect. So we can write that benefit would be lesser side effect. That's what we have studied in a chirality. Or you can write that relatively higher biological efficiency. The disadvantage and another advantage or benefit would be we need a smaller dose, because there is no other isomer in it. It's a pure one. So disadvantage is that they are asking for disadvantage of producing. So the disadvantage is that we get a lower yield of it. For example, if we are preparing it, we always normally get the racemic mixture. So from the racemic mixture, we have to separate the two enantiomers from each other. If we have to separate them, then we will obviously the amount of the pure one gets lower. Okay. Now, P1, name all the functional groups present in perindopril. Okay. So if we go for the functional groups over here, yes, who can tell me the functional groups? How many functional groups and what are the functional groups present over here? If you guys have studied the functional groups in AS, so please let me know what functional groups you can identify in this compound. Okay, which functional group is this? Then this is the second functional group. Then this is the third functional group. And then here it is a fourth functional group. Yes, carboxylic acid. What else? Beside carboxylic acid, what are the rest of the three? It's a carboxylic acid, right? This one is an amine. This one is amide. And this one is an ester. And today, I'm sorry that the net is relatively, it's not working properly. So the screen is lagging. Since I have taken the classes before, the same thing is happening. So see, I think it's lagged right now. So there are 4 functional groups, right? Carboxylic acids, amide, amine, and ester. Okay. Now, next part. See again stepped. Okay. A sample of parent propyl is hydrolyzed with hot aqueous acid. So it means acidic hydrolysis. Draw the structure of the three organic products of the complete acid hydrolysis of parent propyl. So it's better to draw the parent propyl over here. It will make you easy to understand. Or let me see if I do this. Yep. So if we keep it over here, so it's easy to make the hydrolysis products over here. Okay. So amides hydrolyzed, esters hydrolyzed, right? So if you see over here, this is an ester link and this is an amide link. So it is going to break down from these two links. So we get these three parts. So now if you have this structure over here, so it's very easy for you to draw the products. So when it breaks from here, we will get this thing. The center one was, if you see, it is this thing. Now that these are not the complete products, right? I'm just drawing the fragments. And the third one is N with the 5 ring structure, which is bonded to a 6 carbon structure. And over here, there is a C double bond OOH. So is this clear? What I just did, I just put them into the fragments. Okay. And the acidic hydrolysis is there. So this carbonyl turns into carboxylic acid. This is going to turn into carboxylic acid. Okay, my bad. 1 minute, please. Actually, the breakage from here, it will break. So this part would be over here. So here we get the alcohol. Here it's a carbonyl, so it turned into carboxylic acid. Both the sides. See, here we get a H. Here we got OH. Here we got OH. And to this nitrogen, we get a H. See, is this clear to all of you? Okay. If any one of you has any query in this hydrolysis, please ask. Okay. Then question number 7A. Explain why phenol is brominated much more easily than benzene is brominated. Yes, who can discuss the reactivity? It's all depend upon the reactivity. So if you guys recall, in phenol, there is a OH bonded to a benzene ring, right? So the lone pair of oxygen delocalized into ring. So see, now in the ring, instead of a 6 electrons, now it have a 8 electrons in the pi system. So if there are 8 electrons in the pi system, so due to which the pi electron density increases. Right? Hence, it can polarizes electrophile because they all undergo electrophilic substitution, right? Electrophile more easily and gets substitution, if you recall, due to the at phenol because it's an electron donating group. So substitution at 2, 4, and 6 positions. So it will substitute the next group on carbon 2, 4, and 6. No, my screen is again stuck. Now, 5 part B. Iodine monobromide, IBR, reacts with benzene in the presence of an AlBr3 catalyst. So isn't it the same reaction when you just react bromine or chlorine in the presence of AlBr3 or FeBr3? Predict whether the organic product will have bromobenzene or iodobenzene. Yeah, that is a very interesting question. So it's very easy to identify among these two, which one is a more electronegative? Yes, between iodine and bromine, which one is the more electronegative? Yes, wrong, Ahmed. If you recall, the reactivity decreases down the group, so bromine is more electronegative. So bromine becomes partial negative and iodine becomes partial positive. So when the bond is broken, we get I as a positive and Br as a negative. So see, I would become an electrophile and electrophile gets substituted on the benzene ring, right? So that's why I, and Ahmed, please be focused. Because benzene has nothing on it. So that's why benzene does not, brominate more as easily as phenol do. We need this catalyst for a bromine to undergo a reaction AlBr3 or FeBr3 or FeCl3. But for phenol, we don't need it because of the OH group. And the reason we have mentioned over here that the OH has a pair of electron and that lone pair of electron is delocalized or induced in the benzene ring. As a result, the delocalized electrons got 8 instead of having 6, which are in benzene. So which makes it more, more electron rich, or the pi electron charge density has increased. So it can easily, polarize the electrophile over there. Okay. So here, what we are going to write, first we have to predict. So we have predicted that it's iodobenzene, that iodine is going to substitute on benzene instead of a bromine. And the reason is same. That's what I have discussed, that because bromine is more electronegative. Is this clear to all of you? Yes. Now, C part, figure 7.1 shows some reactions of phenol. Okay. Given equation for the reaction of phenol with a sodium. Okay. So for a sodium, if you recall, what happens that H is substituted by sodium and we got a half mole of hydrogen gas. So we have to write the equation over here. So phenol is the formula of the phenol, if you guys recall. it's C6H5OH reacting with sodium, again struct C6H5O negative Na positive and H2. And before H2, I put the half to balance it. Okay, if you guys recall this reaction, in reaction one we use dilute nitric acid, because if we have used concentrated nitric acid, we got the tri-substituted product. And here we got NaNO2 plus HCl or NHNO2 plus HCl. And here it's an excess bromine. So in excess bromine, we get a with the bromine, we get 2, 3, 4 tribromo substituted, tribromophenol. Okay. Now, draw the structure of the organic product are formed when phenol reacts with an excess of bromine. So that's what we have discussed. The last thing, that over here we get a OH, we get one bromine over here, one bromine over here, and one bromine over here. Now, state the reagent and conditions for the reaction 1 and reaction 2 in the figure 7.1. For the reaction 1, we use the dilute nitric acid. So, dilute is the condition and the reagent is nitric acid. For reaction 2, as we have discussed, oh, my bad over here. First, we use this, then, okay, sorry. The phenol is over here and this thing is getting substituted over here. So it means here we were using a diazonium ion. And that diazonium ion is used in with alkaline in alkaline condition or with sodium hydroxide. So for a reaction 2, we are going to use alkaline and C6H5N2 positive. Or either you can draw the whole structure like this and put a positive charge over here. Okay, so we are done with question number 7. Now let's move to question number 8. Describe the difference in reactivity of chloroethane, chlorobenzene with hydroxide. Explain your answer. So with the hydroxide, if you recall, it's a reaction, it's a hydrolysis reaction. So if you recall a reaction of chloroethane, it's going to be C2H5Cl. If we heat it with the hydroxide ion, alkaline, oh sorry, aqueous hydroxide ion. So what will happen? That is the AS base reaction. C2H5OH is formed. But with chlorobenzene, as chlorine also have a lone pair and it overlaps its lone pair with the benzene ring, so that bonds becomes stronger. So it is really relatively very less reactive as compared to chloroethane. Just give me a minute. Okay. So the first statement that we will do, write is chlorobenzene is less reactive than chloroethane with hydroxide It is because the lone pair of chlorine, the same thing. It has a lone pair that is delocalized, or you can say overlapped into the benzene ring. Makes carbon chlorine bond is stronger in chlorobenzene. Is this clear to all of you? Yes, Abdullah, what you want me to repeat? Okay. Now, compound T, C6, C5H9O2Cl. Is a useful synthetic intermediate. Figure 8.1 shows some reaction of a T. Okay. Now, if you recall it with sodium hydroxide, okay, let's see. Give the systematic name for a T. Okay. So if you see, this is a ethyl. This is the alkyl part, right? And this one is a alkanoid part. And this one is a alkyl part. So alkyl part has a 2 carbon, so it becomes ethyl. And alkanoid part has a 3 carbon and a chloro. So we are going to call it chloropropanoate. So the complete name would be ethyl chloropropanoate. And chlorine is on carbon number 3rd. So ethyl 3-chloropropanoate. Okay. Now what they are saying, okay. Draw the structures of W, X, Y, and Z in figure 8.1. Okay. So we are heating with excess sodium hydroxide. So obviously, if we are heating with the excess sodium hydroxide, so as you recall, a hydrolysis will occur and it would be broken down from here. So on breaking of this, we got one fragment this and the other fragment this. So here it will become carboxylic acid, here it will become alcohol. But with aqueous sodium hydroxide, we have discussed that chlorine is substituted by the OH group. So this chlorine also gets substituted. And we get a OH over here. Okay. Now, if you see, okay, in step 1, if you see the Cl turns into CN, so it means uh, it's a reaction with potassium nitrile ethanolic. This is the reaction. That's why CN, it turns into CN. If you see step 2, it would become NO2. The two O are here. So it means that here a reduction must be occur. That's why that C triple bond N turns into, because there are more, hydrogens over here. If you make its molecular formula 1, 2, 3, 4, 5, 6, there are 6 carbons. Now, if you count hydrogen 2, 2, 4, 5, 6, no, 4, 5, 6, 6, and 3 are 9. There are 9 hydrogens and it's NO2. So see, 4 number of hydrogens are being added. So if you see C triple bond N turns into C single bond N. So 2 hydrogens gets over here and 2 hydrogens gets over here. So see, The four hydrogen are justified from 9 to 13. So it means it's a reduction. Okay. And here it's a hydrolysis with excess HCl. So see, alcohol is formed, and over here with acid, nitrile is also hydrolyzed to form carboxylic acid. So this carbon becomes carboxylic acid, and this carbon also becomes carboxylic acid. So we are done with W, X, and Y. Okay, now if this is the case, then see, no breaking would occur over here because it's a reduction of a nitrile group. So it becomes C, and here N becomes H2. So it becomes CH2 and H2 instead of C triple bond N. Okay. Now, reagent for the step 1. So that's what we have discussed. Sodium cyanide reagent and condition in ethanol, and we heat it. Okay, for the next one, we will use LiAlH4, and for its the condition is in dry ether. Now, C part. The proton NMR spectrum of compound T, okay, in CDCl3 is shown in figure 8.2. Okay. So they have shown you the compound, they have given you the peaks and their chemical shifts are clearly mentioned. Okay. So, and they have given you the proton NMR scheme over here. Suggest why CDCl3 is used as a solvent instead of CHCl3 with the proton 1 NMR spectrum. And if you recall, it is because in CDCl3, D does not give a signal. That's why we use CDCl3 instead of CHCl3. Where, Alina, you are talking about 6 or 7 carbons in the previous question. There are 6 carbons and 7th one is a nitrogen. If you see 1, 2, 3, 4, 5, 6, these 6 are carbon, and here it's a nitrogen. So it means there is no carbon over here. This carbon is bonded to the nitrogen. Okay. Okay. So because deuterium has a, which one? This one? Yes, Alina. Yes. So see, 1, 2, 3, 4, 5, and 6 carbons. There are 6 carbons, 9 hydrogen, and NO2. Okay. Complete the table 8.2 for the proton NMR of spectrum T. Okay. Okay. So I think now it's easy to work over here. So if you see the splitting pattern of 1.2 and 2.8 and 3.7, these 3 are triplet, and at 3.9 it's a quadrat, right? Because there are 4 peaks with the ratio of 1:3:3:1. So here we have a quadrat, and these 3 are triplet, triplet, triplet. Is this clear? Now, number of protons. Okay, if you see this one, let me highlight with the carbon. If I'm talking about this one is going to be this carbon because it's a 1.2, which is in the over here range. So it's an alkane. So it's a alkyl next to alkyl. No, I think my screen is again stuck. Okay, then if you see the 2.81, so what I think the 2.81 is a this one. No, sorry, 2.81 is a this one. The two things, as it's a triplet, this is a triplet, so it means triplet means the neighboring carbon has a two hydrogens. So see neighbor to it, there are two hydrogens over here. And this one is a triplet as well. So neighbor to it, see, there are two hydrogens over here. And if you see this one is actually this one. No, sorry. Is actually see this one. It is because if you see neighbor to it, there is a three hydrogens. So due to these three hydrogens, we are getting a quadrate over here. So the 2.81, the one which is at 2.8 is basically this one. Because if you see the alkyl group next to carbonyl has a value between 2.2 to 3.0. And next to electronegative element is 3.224. So see, we are getting 3.9. And one is left, which is at 3.7. So chlorine is less electronegative than, oxygen. So that's why it's also, lesser than that. But see, this one is also lying in this region. Is this understandable to all of you? Let me make it a little lighter. Yeah. Is this understandable? So over here, I'm going to write that it's an alkane and it's this one, right? So it's a CH3 group. So how many protons are these? Three. Then at 2.8, it is this one. And how many hydrogens over here? Two hydrogens over here. And it's a next to alkyl next to C double bond O, right? So I'm going to write over here alkyl next to C double bond O and has a two hydrogens. And then at 3.7, alkyl next to chlorine and two hydrogens. See, it is this one, right? And it has a also has a two hydrogens next to Cl. Okay. And the last one, which is at 3.9, it is due to this one because it's next to more electronegative oxygen and it also has a two hydrogen. So we are going to write alkyl next to oxygen or electronegative atom, and there are two hydrogens. Now explain the splitting pattern of peak at 3.9. So we identified that it's a quadrate, and why the quadrate occurs? It means that uh, it means there are three hydrogen atoms on neighboring carbon. So till here, is this clear to all of you? Now, question number 9, part A, define the standard cell potential. Okay. So we can define it as the potential difference between two half cells under standard conditions. Okay. Now, an electrochemical cell is set up to measure E naught cell of a cell consisting of iron 3 positive, iron 2 positive half cell and a chlorine chloride half cell. Draw a label diagram of this electrochemical cell. Include all necessary substances. It is not necessary to state conditions used. Okay, that's fine. So see how we will do it. We will make one beaker and we will make the other beaker. We fill it with the solutions. We will make a salt bridge. Right? Okay. Then we will put the electrodes. These electrodes are going to connect with each other through a voltmeter. Okay. I'm going to put it as a platinum if the solution has Fe3 positive aqueous ions and Fe2 positive aqueous ions. And as the other one is a chloride and chlorine, so I'm going to put a chloride over here. Okay. And it's an aqueous. And for chlorine, we need a gas, right? So I'm going to make this thing over here. And from here, I'll mention a chlorine gas. And whenever we make a electrode of half cell of a gas, so here we use platinum black, not just a platinum. Is this clear to all of you? So that's how you have to make the whole diagram. And as they don't ask you to state the conditions, so there is no need to write the conditions over here. Now, the cell reaction for the electrochemical cell in B is shown. Okay. The Gibbs free energy in kilojoule per moles. Calculate for this reaction. Okay. So for a Gibbs free energy, if you recall the expression, so it is Gibbs free energy is equals to minus N F times E naught cell, where N is the number of electrons transferred, F is Faraday's, which is 96500 coulomb, and E naught cell is given over here. Okay. So if you see, there the oxidation number of chlorine is 0 and here it's -1, but there are 2 chlorine. So it means the 2 electrons are gained. If you see, it's +2, 2 +3, but it's 2. So 2 electrons are lost over here. So the value of N is going to be 2. Okay. So we are going to put -2. Faraday is 96500. And if you don't remember the value of Faraday, how you are going to find it? Let me show you. And it's positive 0.59. So see, here we got the constants. Here it's provided to you. So can anyone calculate it and tell me the answer, please? Yes, can anyone calculate it and tell me the answer, please? And remember, from this you will get the answer in joules. So it's minus 1.13870 joules per mole. And if you have to convert it into a kilojoule, you have to divide it with the 1000 because they have asked you to turn into a kilojoule. So can you divide it in 1000? You will get minus 113.87. But see, if we have to use the three significant figures, so it is going to be minus 114 kilojoules per mole. Is this clear to all of you? Okay. Now, another experiment is set up using the same electrochemical cell. Okay. In this experiment, Fe2 positive ions concentration is 0.15 mole per dm cube. All other concentrations remains at their standard value. So the half cell would become non-standard. The Nernst equation is shown. Okay. Use the Nernst equation to calculate the electrode potential of Fe3 positive, Fe2 positive half cell in this experiment. Okay. So it is very easy to calculate E. E naught is given over here, which is this 0.77 plus 0.059 over Z. And here Z is the number of electrons in the half equation. So if you see the half equation and if you see over here, the change of electron is only, 3 positive, is gaining only 1 electron and turning into Fe2 positive, right? So the value of Z is going to be 1. So I'm going to put 1 over here. And from these two, it has a bigger oxidation number, so it is oxidized species. It has a smaller oxidation number, so it is a reduced species. So log, they have mentioned that the concentration of iron 2 positive is 0.15. So reduce the species in denominator. So I'm going to write 0.15 over here. So it means that all the other concentrations remains at their standard value. So it means Fe3 positive concentration would be 1. So in the numerator, I'm going to put 1 because Abdullah, that is the thing that wherever we are going to state the answer in three significant figures only. Okay. So we got this expression. Can anyone calculate it and tell me the answer, please? Whenever you have to state the answer, keep the answer in three significant figures. See over here, it's 113.87. Why you are saying 1 and 0.5? Okay, it's 0.15, which is given over here. And see, they are saying that Fe2 positive ions concentration is 0.15. So we have put it over here. Okay. And all the concentrations remains at their standard values. So if the standard values are there, then the other concentration is only 1 mole per dm cube. Under standard conditions, the concentration of each species 1 mole per dm cube. That's what we have studied in electro, right? So that's why. So over in the formula, the equation would be like this, that Fe3 positive ions concentration divided by Fe2 positive ions concentration. Now, as the Fe3 positive ions concentration is standard, so it is going to be 1. And Fe2 positive ions concentration is given over here, which is 0.15. So we put it over here. Okay. So see, the electrode potential values are always in a 2 decimal places, right? It's 0.77. So Ahmed, you got 0.818. So it is going to be 0.82 volt. So I'm going to put over here 0.82 volt. Is this clear? Okay. Now what they are saying, use your answer to D1 to calculate the E cell for this electrochemical cell. So if you recall the expression for the E cell is equals to E reduction minus E oxidation, right? So okay. So if you see, they have given you the E cell, that is the standard cell conditions, right? So let's have a look. In first one, in first case, when the case is first, the E cell is 0.59, right? And if you see from here, iron is in, sorry, chlorine is undergoing reduction and iron is undergoing oxidation because the oxidation number of chlorine is decreasing. So E reduction is a E naught of chlorine half cell, which we don't know as it's undergoing reduction, but the half cell which undergo oxidation is Fe2 positive, Fe3 positive, right? And under standard conditions, it would become X, and this one is 0.77. Under standard conditions, its value is 0.77, right? So from here, we got the value, the standard electrode potential value of chlorine. So can anyone tell me the electrode potential value of chlorine over here? It is 0.59 minus 0.77. What is the answer? 0.59 is the E naught cell of the standard in under standard condition. C over here, it is provided. And under standard conditions, we know the electrode potential of half cell of iron as well. So we put these values to find the half cell of the chlorine. See? Yeah, okay. So it would become plus, sorry. Yeah, what will be the answer now? It's 1.33. So it's the E naught value of chlorine chloride, right? Now, if we have to calculate the E cell under non-standard conditions, so we are going to use the same expression, E reduction minus E oxidation. The chlorine is undergoing reduction and its conditions are standard, so it is going to be 1.33. But iron is undergoing oxidation and iron has a non-standard condition and its electrode potential is half cell potential is 0.82. So 1.33 minus 0.82. After this, we are going to use the expression again, and now we are going to use the electrode potential of a chlorine and oxidation of the non-standard condition half cell value of iron as well. Can anyone tell me the answer? It was 1.36. Are you sure? Yeah, it's 1.36. Okay. Yes, now calculate it 1.36 minus 0.82. We are getting 0.54 volts. Okay. Yes. So here this paper is completed. And we are done with May, June 2023 for two. So in the next class, I'm thinking that we will start a winter 23. What is the date of paper 4? 8 May, yeah. Okay, so we will start. Okay, then we will do the another variant of May June 2023. Then we will move to the October November, and then we will after that we will going to do the February March 2024 inshallah as well. Okay, so see you everyone tomorrow. Take care. Allah Hafiz.